So organic analysis is the final part of the AS organic content. It comprises essentially three parts, two of which we're going to look at in this presentation. So the first thing that we're going to look at is infrared spectroscopy. So it's a way of discovering whether particular compounds have certain functional groups based on their absorption of infrared radiation. We're going to also consider high-res mass spectrometry. This gives us greater detail than the mass spectrometry you've looked at up to this point. And then finally, the third part of organic analysis, which isn't going to be in this presentation, are the tests for different functional groups. So when we did alkenes, we did bromine water. In the section on alcohols, when we made ketones and aldehydes, the way we could distinguish them was through Fehling's solution or Tollens reagent. And then we can also test for carboxylic acid using something like sodium carbonate or sodium hydrogen carbonate, and we can see if there's effervescence or not. So we're going to start with infrared spectroscopy. So just in the bottom right-hand corner, we're going to see a lot more of these examples of these in the rest of the presentation, but in that bottom right-hand corner, we can essentially see what is an infrared and IR spectra for a particular molecule. So this is just a reminder that infrared radiation is one part of the electromagnetic spectrum. It's a spectrum where we go from low energy, so radio waves, all the way to high energy gamma rays. We've briefly looked at ultraviolet when we were considering the depletion of ozone in the halogenoalkanes topic due to the formation of chlorine free radicals from CFCs, because ultraviolet radiation transferred enough energy to break the carbon-chlorine bond. So now we're looking at infrared, and this time we're considering it in terms of how its absorption might tell us something about a compound. So actually there are many regions of the electromagnetic spectrum that can be used to tell us something about molecules and atoms. The ones that we look at A level, in year 12 we look at what we're about to do now, which is infrared and infrared spectroscopy. In year 13, or in the year 13 content, we will look and consider radio waves and NMR spectroscopy. So we don't really look at ultraviolet and visible at A level, but they are still regions of the electromagnetic spectra that can tell us something about chemical substances. So the equation at the top of this page isn't really that important for this topic. It is something that we'll come back to in year 13. But you're hopefully not surprised to discover that E represents energy. Nu is represents frequency. And then the H is Planck's constant, which is the smallest unit in science. It has a value of 6.626 times 10 to the minus 34, and its units are meters squared kilogram per second. So the whole equation is known as Planck's equation. It's something we look at briefly when we look at transition metals in year 13. It's not something we need to know now, but it's just to relate energy with frequency. All right, so the key thing is that molecules absorb energy from infrared radiation, and that shouldn't surprise you, because that's what lies behind the greenhouse effect. So when you did your GCSE and you did chemistry of the atmosphere and you did about the greenhouse effect, one of the things that you were looking at was that infrared radiation that was radiated from the Earth was absorbed by the greenhouse gases, such as methane, carbon dioxide, water. Those were the three main ones that you had to be aware of, but there are many, many others. They absorbed that radiation, and then they emitted it again, and emitted it into in different directions. So some of it was essentially trapped. We're just considering here the actual absorption. And when molecules, or when bonds, it's really the bonds that absorb the energy. When they absorb that energy, there can be different types of vibration that are a consequence of that absorption. So the examples that we've got here, we could have a symmetric stretch. So what's happening is the bonds are sort of stretching inwards and outwards at the same time. It's like a symmetrical stretch. So they're coming in at the same time, going out at the same time, coming in at the same time, coming out at the same time. Then we've got an asymmetric stretch. So one might be going out and one might be coming in, and then vice versa. And then bending is really about them moving, not getting closer or further away from the other atom. So not sort of like a spring in that sense. That's one way to think about those other two, is the springs being compressed and released, compressed and released. These are sort of bending, maybe bending upwards or downwards. But the whole point is the energy is absorbed, and that causes various types of vibration. What you may have known or realised or been told at GCSE was, or you may have considered, that all of the non-greenhouse gases were the elements, were like oxygen. I mean, there's 21-ish% of oxygen in the atmosphere, 78-ish% of nitrogen in the atmosphere. They were not, and they are not, greenhouse gases. So for a molecule to absorb infrared radiation, one of the things it's got to have is a change in dipole moment. There's got to be something there already. So there's got to be a difference in electronegativity, essentially. So that's one of the things that we might be considering or thinking about when thinking about infrared absorption. So we find that the more polar the bond is, the more intense the peak is, i.e. the more IR radiation that's been absorbed. We can also think about symmetric and molecules. They tend often to be non-polar, so they'll have weak peaks. And the frequency of infrared radiation, if we think back to that electromagnetic spectra that we saw earlier, it was quite a broad wavelength or broad frequency, range of frequencies or wavelengths in the IR area. And which particular frequency is absorbed is going to depend on the bond itself. And it's this that allows us to identify what we think of as the key functional group. So we've been doing compounds up to this point. We've been considering them as families. We've looked at things like alkanes, alkenes, halogenoalkanes. We've thought about alcohols. That alcohols has just introduced us to the idea of carbonyls, so ketones and aldehydes, and has also introduced us to carboxylic acids. And so IR is going to help us identify some of those key functional groups. So we're going to look at some spectra in a short while. One of the things that we're going to notice, and you may have seen this on data sheets as well, that you've used in tests and things that you've done so far, is we're going to be looking or thinking specifically about the wave numbers or wave numbers of peaks. Well, they're not really peaks, they're actually absorptions, but they're going to look like inverted peaks or upside down peaks. That is simply 1 over the wavelength of the radiation absorbed. And we'll find that the range of wave numbers that we're going to consider, in fact we won't get anywhere near 4,000 to be honest, but is between this range, or our spectra is going to lie between the range of 4,000 to 400 centimetres to the -1. We're really going to be focusing our attention above 1500, because that is the area in which we can identify specific functional groups. Below 1500 is not going to be important to us, but it is important in general because it can be used for fingerprinting, i.e. it will have a pattern that is unique to every molecule. So we're just going to cover that fingerprinting region just very quickly. It's very complicated, it's very crowded, there are lots of signals, it's very difficult to pick out functional groups. On your, as we'll see shortly, on your data sheet, it will have a couple of wave numbers in that region, but they are essentially a red herring. You're not going to use them. It is unique for every compound, so that's why it's got this name fingerprint. You can use it as a way of identifying a compound through whether it has an exact match with something that's already known. And you can also use it to check if a compound is pure. But as far as we're concerned, for A-level, other than understanding that it is a fingerprint region, other than understanding that it's unique for every compound and what do we mean, therefore, by fingerprint region, there is very little that we have to do with that part of the spectra. So this is taken from your data sheet that you get in an exam. So it's got this table here. Some of these, well, as we can see, there are a couple down at the bottom that are in that fingerprint region. So the carbon-oxygen bond, for example, and the carbon-carbon bond. We are never going to use those. They are never going to appear. The most common by a long, long stretch are the carbonyl group, the OH for alcohols, and the OH for acids. Okay, so they are by far the most common, and we will be also considering the carbon-carbon double bond, and just occasionally amines crop up. Why are we not interested in the carbon-hydrogen? Because basically every molecule we look at is going to have a carbon-hydrogen bond, so it doesn't really tell us anything. I haven't yet seen a nitrile peak come up, but that's not to say it won't ever. So, but you know, if we understand the principle behind what we're doing, it shouldn't really be a problem that we have very little practice on a particular absorption, such as the carbon triple bond nitrogen. So this page is just really a translation of the data or the wave numbers on the data sheet that we were just looking at, and this is just focusing on the four most common absorptions that we're going to consider, and just are representing them in a slightly different way. But essentially it's the same information. So we're going to be using this to just go through a couple of molecules and to just identify their functional groups to make sure they're there based on the spectra, and hopefully things will start to become clear to you. So just before we look at this molecule specifically, I do want to just highlight now at this point, because it's always going to be there, this carbon-hydrogen peak. So you'll see it's in the region 2,850 to 3,300. It is this absorption here. And so this actually will feature in every spectra that we see from now on. Now we are told in this example, we are told that this is hex 2e, and we can see that there's a carbon-carbon double bond in the skeletal structure there in the bottom right. So we are looking for, we should be seeing, an absorption for carbon-carbon double bonds. So it's in the region 1620 to 1680. So this is a really small absorption. So you are going to find that the carbon-carbon double bond absorption is always, it's quite subtle, all right? I mean, you can see there's large regions of space here, and if we look in that region that we've been told, 1620 to 1680, it's not a very large region. There is a slightly more noticeable peak, the one I've done in green, but it's not abundantly clear. So you're going to have to be careful and look for that. Take care when you're looking for it. So here we have a different alkene, cyclohexene. Just going to, for the moment, confirm to you, look, there's our carbon-hydrogen. It's there. Okay, it does look different to what it looks before, but it's in the same region. It is quite a jaggedy absorption, which we'll notice. So again, it's an alkene, so we should be looking for our carbon-carbon double bonds. It should be in that region 1620 to 1680, and there it is. Okay, again, quite subtle, but it's definitely there. Again, I'm just going to do the carbon-hydrogen. The reason I'm going to do that is when we look at carboxylic acids in a minute, it's going to just help us understand something or appreciate something. But anyway, we are looking at propan-1-ol. We are looking at an OH group, and we are specifically looking at an OH group in alcohol. So if you're ever identifying a compound and you know it's an OH in an alcohol, you must absolutely say it's an alcohol. You cannot just say it's the peak or the absorption, is due to an OH bond. You must be specific about what type of compound it is. So it's in that region 3,230 to 3,550, and it is this large absorption here. So it's very noticeable. Okay, and that is our alcohol absorption. And we've got butan-2-ol, so again it should have an OH group that's from an alcohol. It's in that region 3,230 to 3,550, and there it is. They really stand out. Alcohol absorptions really stand out. So this time we've got a carboxylic acid. Now the carboxylic acid has an OH group in the same way that an alcohol group does, but it is at a slightly lower wave number. And what we get is a really, really broad peak. Now the reason it looks so broad is that in effect it has merged. You'll see that there's an overlap. If you look at those two sets of wave number regions with the CH and the OH, you'll see that there's an overlap between them, and that is why we get this really broad peak, because essentially they've merged together. Okay, but as far as you're concerned, this is our OH group from an acid, carboxylic acid. Now if it's carboxylic acid, that means it also has a carbonyl group. Okay, so then there's 1680 to 1750 range, and you'll find, here it is here, you'll find that this is typically a very strong absorption, so normally stands right out. Here's a different carboxylic acid, so there's our region, and there's our carboxylic acid, or OH from our carboxylic acid, sorry. We've also got to have had the carbonyl, and so there we get. So you can't have the OH acid absorption without the carbonyl, because it's not a carboxylic acid if it doesn't have both the carbonyl and the OH group of the same carbon. So propanone is there's an aldehyde. The only functional group is the carbonyl group, is that C double bond O. It's in that C double bond O region of 1680 to 1750, and that's what we've got there. So we don't have that big broad peak we had from the carboxylic acid around the 3000 plus mark, but we do have our carbonyl. This is an ester, but again the key functional group in an ester really is the carbon double bond oxygen, sorry, which we have very clearly. It would have the carbon oxygen bond, but as you can see, that's in the fingerprint region. It's 1000 to 1300, so it's not something we ever have to look for or identify. It's just too difficult to do so. And here's an aldehyde, so no different than a ketone in the sense that it has a carbonyl group as its functional group. It just happens to be at the end of a chain rather than in the middle of the chain. That doesn't really make any significant difference in terms of the absorption of infrared radiation, and so there is our C double bond O. So we're going to just look at some functional groups. So I'm going to show the slide. I suggest you pause it. I suggest you then try and think about what functional groups you can identify. So you don't have the molecule in front of you. You're just simply trying to find out whether this is an infrared spectra that shows that whatever we're looking at is a carboxylic acid, and how you know whether it's got a carbonyl group, whether you know whether it's an alcohol, whether you know whether it's an alkene, whether you know. Okay, so I'm going to show them. I want you to pause them. I'm just going to leave a couple of seconds anyway, gap, and then I'm going to just highlight what we could have concluded from each of these spectra. Okay, so pause the video and try and decide which functional groups you think are shown on this particular IR spectra. So one that jumps immediately out at me is this large peak here towards the left. If we look at the wave numbers on our data sheet, we will see that that is an OH group and it is an alcohol. And you must specify that it's an alcohol, otherwise you just won't get the marks. There doesn't seem to be a peak that relates to a carbon-carbon double bond. There isn't a peak that relates to a carbon double bonded to an oxygen. And so that is it. All we can tell from this is that we have an alcohol. We don't know whether it's primary, we don't know whether it's secondary, we don't know whether it's tertiary. But this would be a piece of information that we would have, and they would give us, and then there would be questions that supplied us with other bits of information that would allow us hopefully then eventually to work out or deduce what the actual compound was. So here's the next one. I'll let you again pause the video, have a little think about it. So there is a bond that jumps straight out, or an absorption, sorry, that's jumped straight out, and that's this one here, and that is clearly a carbonyl group. Okay, so we don't know what it's bonded to, but it's a carbonyl group. Have a look at this one, pause the video. So we've got a very strong absorption here, and we've got a very strong absorption here. So that tells me that we definitely have a carbonyl group, and also that we have an OH group that is an acid, carboxylic acid, so we must say that. And there's no evidence of a carbon-carbon double bond. So again, pause it, have a think about it. Okay, we've very clearly got an absorption here. And so that is an OH group alcohol. Again, okay, have a look at this, pause the video, have a think about what functional groups you think are present. Alright, so we have definitely got a large absorption here. And that is well, we know that's now an alcohol. Okay, but it's not the only absorption we can see. We can see that there is also a strong absorption here. Okay, that is a carbonyl. Now, this is quite important because quite often if people see an absorption on the left-hand side of the spectra and a carbonyl present around 1700, they automatically assume it must be a carboxylic acid, but this isn't. This has two separate functional groups. It has an OH from an alcohol, and it has a carbonyl somewhere else. It could be an aldehyde or a ketone at that part of the molecule, but we don't know. But they are two separate functional groups, and you've just got to be wary of that. You've just got to not assume that if you see a carbonyl and an OH, it must be a carboxylic acid. You've got to look at the evidence, you've got to look at the absorption wave number, and you've got to be really careful about that. Okay, have a look at this one, and then pause the video. Okay, so we have a strong absorption just here, and that is clearly a carbonyl. Have a look at this one. Pause the video. Okay, so there's no obvious OH group, there's no obvious carbonyl, and we're almost looking at this thinking, well, is there anything? And this is where we've just got to be a little bit careful, because it's quite easy to miss sometimes a carbon double bond. It's never a strong peak, ever. So the carbon-carbon double bond, just be very careful that you don't miss that. Right, so again, pause the video, have a think. So we have a strong absorption here. Okay, so that is an OH from an acid. And of course that means we must have a carbonyl, which we do. We can see that strong absorption here. So we have a strong absorption from our carbonyl as well. Again, pause the video, have a think about it. We have a very strong absorption here. We don't have anything in the 3000-ish region of any note, because don't forget that jaggedy spike is always a carbon hydrogen. So we only have a carbonyl group here. Okay, again, have a look, pause the video. So this is an unusual one, actually, because and it's not terribly clear really from the wave numbers, but I think this one is really supposed to be a carbon double bond. Now the ones that you get in an exam I think will be slightly easier to be certain about the wave numbers that you're looking at, and this is a strong peak, and I've been saying that they're not really strong peaks, typically carbon-carbon double bonds, and I think in your exams it will be clearer than we've got here, but this is in fact a carbon-carbon double bond, due to exactly where the absorption is. So we're moving on to high-res mass spectroscopy now. So there's just a little reminder of our time of flight mass spectrometer. I'm not really going to go through that side of things at this point because that was done earlier in the course, and that's something if you need help with, just to ask me separately. If you think back to the periodic table you used at GCSE, they were all integers. All of the mass numbers, were integers. There were only two elements that you saw that didn't have a whole number as their mass number, and they were chlorine and they were copper, and they were 35.5 for chlorine and 63.5 for copper. And they were really there to help illustrate the idea of isotopes, the fact that you could have the same element, therefore you had the same number of protons and electrons, but you could have different number of neutrons, and that's how we could have a mass number that wasn't a whole number, because we were talking about the relative atomic mass or the average atomic mass of an element. When you got to A level, now your periodic table was to one decimal place, and hopefully you became aware of the fact there were many elements which didn't have a whole, like a whole number or a whole integer had an integer for their mass number. So there was, for example, calcium, 40.1. But even that is more precise. The A-level periodic table is more precise than clearly more precise than your GCSE one, but it still isn't a terribly high level of precision. If you look at carbon, for example, on your A-level periodic table, it has a mass number of 12.0, but there are three isotopes of carbon: carbon 12, carbon 13, carbon 14, and carbon 14 is very important because that's the isotope relevant to carbon dating. So it's just really what we're seeing here is a level of precision, and we can be so much more precise with our masses than we currently are, or than we are with our A-level periodic table, for example. And it's when we use high levels of precision that we would be able to distinguish molecules that we wouldn't necessarily be able to do if we just relied on our A-level periodic table. So here are some examples where, using our periodic table, we would decide that they all had an MR of 60, and so we wouldn't be able to distinguish them based on that simple mass number. But if we increase our level of precision, we go to 5 decimal places, for example, they would all be rounded to 60 if we were just rounding them to a whole number. But we can see that there are clear differences between them in terms of their mass. And that's one of the things that high-res mass spectrometry allows us to do. So that resolution is much higher, the precision is much higher, and we can be much more accurate in finding the MR, and that can help us distinguish between different molecular formulae. Okay, so we're going to just consider something called fragmentation. If you think back to the original time that you did time of flight mass spectrometry, and you think about the fact that we needed a charged particle, we needed the thing that we were analysing to become a charged particle, because otherwise we weren't going to be able to accelerate it and we weren't going to be able to detect it. And the way that happened with smaller molecules was to fire high energy electrons, which would knock an electron off, resulting in a knock an electron off our original molecule or substance, resulting in a positively charged particle. Now, if you think every molecule, and I'm just going to talk about molecules because we are talking about organic chemistry here, the electrons in every molecule are paired up. They might be a lone pair, or they might be a pair in a covalent bond. And we're talking about knocking one of those electrons off. Now, if we knock an electron off, that means one of those pairs in that molecule must become a single electron. And we know what a single electron means. We know it means a free radical. So really, the species that we're accelerating in a time of flight mass spectra is a positively charged ion, because we've knocked an electron off, but it's also a free radical. Now, there's a lot of high energy bombardment going on, so covalent bonds can break, and if we're breaking our positively charged free radical species, then it's going to break into two fragments or two parts. One of those is going to carry the positive charge, and one of those is going to carry the unpaired electron. Now, what is it that we're actually measuring when we do mass spectra? It's the MZ, right? So if we remember what MZ stood for, so the M was the mass and the Z was the charge. So the only thing out of these two species, the X plus and the Y free radical, that would actually then get detected, because it's the only thing that would get accelerated, would be the X plus in this example. So that would have an MZ value. The free radical would not be accelerated. It's not a charged particle, and so we wouldn't end up with a peak or a detection, for that particular species. Now, molecules can fragment in different ways. They don't. There are places where they're more likely to fragment than not, but we will end up with what on the surface might look like quite a complicated mass spectra, and we just want to think and consider how we can sort of analyse that mass spectra, which is really what we're looking at now. So there are more common types of fragments than others. So carbocations, we've looked at carbocations in alkenes primarily. We can have something called acylium ions, so the RC double bond O fragments. They're pretty common. Basically, the more stable the ion, the greater the peak intensity. So the size of the peak isn't going to tell us the information like it has done when you've done the course earlier, because right at the beginning when you did time of flight, you were considering the peak as a relative abundance. We're not really going to be concerned about relative abundance here. We're going to be concerned about the masses of those fragments, but they are more likely to be visible the more stable the ion is. So we're just going to look at some examples here. So we're starting with butane. When we put butane into a mass spectrometer, it's fired with high energy electrons, and electrons removed, we end up with our free radical positive species. That can then fragment. Okay, so we got on the next line, we're fragmenting. So basically, the molecule in the second line is essentially breaking where I'm doing the squiggly line. So in this example on the second line, we're ending up with a methyl free radical. Okay, there's our methyl free radical there, and we're also ending up with a propyl ion. Okay, and it's the ion that's going to get detected because it's the ion that's going to have an MZ value, and it's going to be 43. Now, to be honest, equally, this fragmentation the same fragmentation could happen where the methyl group ends up being the positively charged species and the propyl group is the radical. But we're just giving examples here of possibilities. On the next one down, so the third sort of the third line, the third sort of equation, we've got our butane breaking up into two ethyl groups. One of them is a positively charged, one of them is a free radical. So on the second one, we are breaking right in the middle, where I'm doing my squiggly line there. And we're getting an ethyl group that's positively charged, which we would detect, and that would be an MZ value of 29. And then we would get a free radical, which wouldn't give us a peak at all. So that MZ29 is supposed to represent that ethyl group there. And we've got to be just aware that, and again, this does hark back to what you did right at the start of the course. We've got to just be aware about how isotopes can produce different signals. So, typically it's halogens we're thinking about here, and that would make sense because we could be looking at a halogenoalkane. And if you think about our halogenoalkanes, we have to take into account that some of them, if it was a bromo halogenoalkane, we could have the bromine could be bromine 79 or bromine 81, and the same with a chloroalkane. It could be chlorine 35 or chlorine 37. So we're going to get a even more complicated spectra because of the fact that there are these isotopes. If it was a really detailed mass spectra, we would probably find that with lots and lots and lots of very small peaks, and they would be due to hydrogen and carbon-13 isotopes. Their proportion, their percentages are really tiny, so they really would be very small bumps almost in the spectra. So not terribly confusing in that respect, other than the fact that they were there. But with the bromines and the bromo compounds and the chloro compounds, we would see something that was much more stark. So this is just a very simple molecule, bromomethane. So we could have, or bromomethane could have a bromine 81 or a bromine 79. So we could have two very different MRs. We could have an MR of 96 and an MR of 94. Of course, if we were doing this just on a molar basis, we would have an MR of 95 because we would have used the relative atomic mass. But here we're almost sort of considering them as individual molecules, even though there might, or the abundance of different molecules. So we've got those two peaks, two apart, essentially because we've got those two bromomethanes, one with a bromine 79 and one with a bromine 81. Here, their abundance is 50-50, so we can, whilst we can't compare the 94 and 96 with the 15 in terms of their height, we can compare the 94 and the 96 relative to each other here. Sort of similar type of molecule, chloroethane. This time we could have chlorine 35, chlorine 37. They don't come in equal abundances, of course, so if you remember, chlorine 35, that was about 75% of all chlorine atoms, and chlorine 37, about 25% of all chlorine atoms. That's why we had an AR of 35.5. If we look at our molecular peaks here, we've got this the 64 and we've got the 66 due to those two different chlorine isotopes. And of course they can each fragment in their own way, which is why we get the 49 and the 51 when a methyl group is removed. And so our spectra now looks a little bit more complicated than we might have thought. This dichloromethane is still a very simple molecule, but it's raised the stakes a little bit by having two chlorine atoms. So we can remember the probabilities that you could have when you just considered chlorine and the different relative peaks, and remember when it was the diatomic molecule, you had peaks of 9 to 6 to 1 in terms of their relative abundance. So that is also something that we could witness here too. And I'll let you just look at this one, consider this one. Again, when you did bromine, and when it was the diatomic bromine molecules, you could have a 1 to 2 to 1 ratio in the abundance. Here we've got molecules, dibromomethane could have two bromine 79s, or a bromine 79 and a bromine 81, or two bromine 81s, and that's going to obviously affect the mass spectra. This is just a different example. This is just considering the fact that the fragmentation can happen in different ways. If you remember that earlier, it said about the acylium ion and how that was particularly stable. So we could have a break here, or we could have a break here. And if we had the former, if we had the green one, we would end up with a molecule, this one here, or we could end up with that species, assuming it was the positively charged one. And if it was the blue, we could end up with this one here. So, it's not a big deal, but just consider about where breaks can happen when you're looking at different mass spectra. And I'll let you just have a look at this one. Take your time, maybe pause the video, just consider it. And then if you've got any questions, just ask me. But otherwise, that is the end of the Year 12 organic content, or not the Year 12 organic content perhaps, but the AS organic content. So fantastic, and congratulations.